Right. So before moving on, let me mention something that I forgot earlier. So when we have the coupling between dark energy and the dark energy field and matter, there were two ways to hide the problem with baryons under the carpet. One was to introduce screening, basically with over density, the coupling, the effective coupling that is touching the equation of motions of matter is negligible. Therefore, the problems with baryons is not there. And automatically also the constraints on the local measurement of gravity are respected. Okay? So everything is solved in this way. Or this doesn't solve completely the local measurements, but you can split the coupling into terms. You can have the coupling for dark matter, which remains in place, no problem with spectroscopic observations, for instance, and another coupling for baryons, which can be 0. We just set it to 0. Now, here is a caveat, because if you are doing to do that, then you don't have, you have to treat matter and the dark matter and the baryons differently, because they have a different equation of motions, right? Because we had the continuity equations that had the terms that they had, and then they had the coupling term here, whereas here we have the very same expression, but with a 0, and these are two different equations. So the equation of motions of these two guys are going to be different. And therefore, if you do that, yes, you solve these problems, but remember that you have an additional equation that you need to solve together with the others. Okay? Just that, I forgot to mention that. Now we make a change of topic, so we're going to move forward. And we enter in the realm of modified gravity. And the first topic that I'm going to cover with modified gravity are going to be conformal transformation. That gives you a mean to express modified gravities as a couple quintessence model. And if you want, you can start with a couple quintessence model that we studied so far into a modified gravity theory. Okay? It's a way of making this sort of transformations, and is one of those mathematical tools that you can use to remove the coupling from one of the species of the universe, for example, baryons, and transfer those modifications into other terms. Okay? You can think of, this is just an analogy, don't take it too literal, but is equivalent of having G mu nu equal to 8 pi G over C to the power of 4, and then you have the energy momentum tensor. You can introduce a modification of gravity by introducing GR, or you can bring in on the other side and define a fluid and have a modified fluid. Okay? So you can have modified gravity or a modified fluid. So the conformal transformation goes in this sort of way of thinking, but it is of course a more mathematically powerful tool. Okay, that allows you to do more things and more transformations. Okay, good. And it's not only dealing with the cosmological constants, but actually with the scalar fields that we are dealing with. Okay, and in general, this population of theories that we are going to discuss are called scalar tensor theories. Okay? Tensor, you know why? Because one of the fields for which we have an equation of motion is the metric, and that's a tensor. And scalar, because we have a scalar field now in place. They can have the meaning of a modification of gravity or the meaning of a modified fluid, perhaps with coupling terms. Okay? Good. Now, let's start with the first tool that we need, which are conformal transformations. Conformal transformations that are quite simple. It's just a linear transformation for our metric. So we have a transform metric, which is just given by this expression. Okay? So you start with your initial metric, you multiply it with a scalar function. That's it. Remember that this is a field, and the field in general can be different as a function of time. For example, dark energy is evolving as a function of time, and if you want to be even more general, might even depend on the position. Okay? That's in full generality, and you get a new metric. Why still a metric? Well, we are just multiplying f times g. It's still a tensor. Okay, we are just rescaling the values of the coefficient of our tensor, and for example, is expressing a scalar product still. Scalar product, which you know, the metric is the tensor expressing the scalar product between two four vectors, and this is respected. The only thing which is changing is not the angle between the vectors, between two vectors, but just their amplitude. Okay, just the result of the scalar product is going to be rescaled. Okay, so no modification in the angles. Between vectors. Then is not going to change the signature. What we need to have that the function is invertible, okay, always, and then the inverse of a function is 1 over f. It means that f cannot be 0 anywhere, otherwise we would have a singularity, okay? F invertible, okay, so the inverse should be always a real number. Good. Then you understand that if we have this additional quantity that can depend on the space-time, can be space-time dependent, it can be used to introduce a new degree of freedom, which is given by our field phi. Not always, okay? We are going to see that that's not always the case. And what else? And that's it. So these are all the properties that this transformation is going to do. It's a frame transformation that respects all of that, okay? And of course, you must also have the inverse of the metric must be still invertible, otherwise you will get singularities and you don't want that. Why do we need something like that? I already have mentioned, because it can be used to generalize this sort of trick. And the main applications are two. One is to simplify your life. You might use them to simplify the expressions that you get. Okay, if you don't use the right one, you just make your life even more complicated. Okay, so with some specific transformation, given the specific problems that you have ahead, it can help you to simplify your lives. Or it can be used to introduce modification in gravity. Okay? And you can kind of see clearly where this might come from, because now the metric is affected. You might introduce a coupling with the Ricci tensor, therefore. Okay? Good. Let's see the key relationships that I'm going to list here. Then it's easy to derive them. They're a very simple exercise to be done. The first one that I'm going to show you is just the inverse of the metric, which guess what it is? That's f to the minus 1 times g mu. That's it. That's the inverse. Then you have another interesting relationship, which is the square root of the trace of the metric, which we always need for the invariant 4 element, right? When you use the action, you have always this square root of minus the trace of the metric, which is equal to f to the power of 2 of minus g. Why f to the power minus 2? Why we are not just multiplying f? Remember the definition of the trace. Because if we have our transformed, conformally transformed metric, that's going to be equal to f phi, and then we have g mu nu, right? G mu nu, which is something can be expressed with a matrix 4 by 4, and the trace is here. You made a multiplication of these factors. So times f, times f, times f, times f. That's an f to the power of 4 that we brought up here, and therefore that's an f to the power of 2. Okay, that's the reason of this f to the power of 2. Then something, yeah? Huh? It's symmetric. The metric is symmetric. No. If you have the Minkowski space, then yeah, but I mean, otherwise it can be, it's just a, I mean, this is coming from this guy, so the metric expresses the scalar product. And it must be symmetric because of that, because it's coming from a quadratic expression. Okay. Good. From the definition of the 4 element, there you see it immediately. You can prove, you can show that it must be symmetric. Okay, good. So we can continue, and we have, we are touching the metric. What does it mean? That we have the Christoffel symbols that are going to be affected. And if we are touching the connection, the Christoffel symbol, if we are dealing with GR, the connection in general, then we are affecting the covariance derivative that depends on the affine connection, right? And therefore, we are going to have something modified that is here. But we know that for a scalar function, that's the case, right? Because the scalar function is insensitive to the affine connection. So it is just equivalent. So the covariance derivative of a scalar function is equivalent to the standard derivative of a scalar function, and therefore you have this relationship. Okay, that's for scalars only. Okay, for scalars only. Because in fact, if we go for the box operator, which has, g mu nu with delta delta, with the mu at the same level, such that they get flipped, right? So if we get the box operator, this is affected, because we have the metric which is actually acting on the derivatives, and we have a net contribution, which is non-zero, and therefore we have a modification. Again, that's a very simple exercise, and the expression is this one. So you see, we have the original box plus additional terms, okay, where this W is defined as that. To f, okay? Again, remember that f is a function of phi, therefore we have the chain rule of derivatives that we can apply, and we can as well write it in this way. right? Just the chain rule applied, so you can have also this expression. So that's our box operator. And then for the Ricci scalar, again, this is going to be affected because the Ricci scalar, you know, depends on the metric. And if we are using a conformally transformed metric, this guy is going to be changed as well. Okay? Again, simple substitution using the contraction of the Riemann tensor using a conformally transformed metric, so it's just brute force mathematics. We arrive at this expression. And you see that the Ricci tensor in a conformally transformed matrix is related to the Ricci tensor of the original metric with these additional terms. Okay? So again, just brute force to derive these quantities. Okay? Good. Now, it's interesting to look, for example, what is the impact of such a conformal transformation on the electromagnetism. Okay? On the Lagrangian, for example, of electromagnetism. Is it going to affect the equation of motion? Let's see. Let's see what's going to happen. So we get the Lagrangian describing our electromagnetic field, which is going to be minus G, F mu nu, F mu nu, right? Standard expression. Then what we can do? We can, let me rewrite it again, like this, minus G, and then a little bit more space, and a little bit more space. What we can do? We can multiply times the inverse, times the inverse, times twice the function. I haven't done anything. I multiply by f squared, I divided by f to the power of minus 2. Okay? But rearranging the expression in this way, you see that this is actually equal to minus G. You see? This guy here is the conformally transformed, the conformally transformed square root of the trace. And these are going to be, again, acting on the others, and we have our, wait, let me use a G mu nu, which is wrong. So G alpha beta, G alpha mu, G. Ah, damn it. Let me, sorry, stupid step, but then it becomes non-clear. So let me do it again. So that's equal to, let's make space immediately, minus G. And then what do we have? We have F mu nu, F alpha beta, and then we have G alpha mu and G beta nu. Okay? I just introduce the metric explicitly there. Then I do the trick. So I'm going to multiply f to the minus 1 here, f to the minus 1 here, and f to the power of 2 here. Okay? So you see, this is the conformally transformed square root of the trace of the metric. Then we have f mu nu, f mu nu, and f alpha beta, which are not affected, whereas these guys are going to be the conformally transformed metric components. So we are going to have G alpha mu and G beta nu. Now look at this expression and at this expression. The Lagrangian is unchanged. The Lagrangian is completely unchanged. Electromagnetism is conformal invariant. Conformally invariant. We get, out of this Lagrangian, we get exactly the same equation of motion. Same equation of motion, which are the Maxwell's equations. What does it mean? If we think in terms of an interaction between our field, phi, and electromagnetism, there is no coupling. No coupling. No coupling between phi, which is contained in the conformal transformation, and radiation, which is what we had before with the coupling that we have chosen earlier. Okay, that's quite a cute result. Okay, let's move on, and let's give a look at the Lagrangian describing our universe, which is the one in which we have a scalar field for our dark energy, we have matter, and we have radiation, but I will just consider a matter component for simplicity. And let's see what happens when I apply a conformal transformation. Actually, there is not the time. But I want to give you the concept. Do I manage so little? Let's try. Okay. So let's take our model in which we have a scalar field and a matter component. Matter component which could be radiation or dust or whatever you want. Okay? And I will set 1 over 6 pi g equal to 1, just not to carry around this annoying term. So for our Lagrangian, for such a system, we are going to have our invariant volume element, which contains our beloved square root of minus the trace of the metric. And then we have the Ricci tensor that is telling us we are in a curved space-time. Okay? And therefore here we might have embedded the metric associated to the Freeman-Lamette, Robertson, and Walker. Then we are going to have the Lagrangian of our scalar field, that of course depends on the metric, and depends on the properties of the scalar field. And then we are going to have the Lagrangian of the matter contribution, again depends on the metric, and the field describing matter, right? It's an ideal fluid, and an ideal fluid is a field, is a scalar field, that is distinguished with this different psi. Okay, so this is dark energy, if you wish. That's the field describing matter. You could write matter here. Okay, nice. This is called the Einstein frame. It's called Einstein frame because gravity is the usual one. We have the Einstein-Hilbert action. Okay? Einstein-Hilbert action, Einstein frame. But now I can do something funny. which is to the omega to introduce our a conformal transformation and remove it. Introduce my f to the power of whatever I need, and I divide by f to the power of minus what I need. Okay? Such that I have, I'm basically not going to touch the theory, but just a rephrasing of everything. Okay? Therefore, this G, by definition, is that. Okay? So this is exactly that. I didn't change anything. I just introduced a conformal transformation of this guy here. Okay? That's what we get. Okay? Oh, there is a minus. That's the inverse. Minus 2. And then we have the other terms. And in the other terms, I'm going to multiply f times I'm going to express R with respect to the conformal R. Conformally transform R. Remember before we had a relationship where we have a R conformal, a pile of stuff with the original R inside. I'm just reinverting this equation to have the original R written in terms of a conformal R. Okay? Therefore, what we get is the transformation that we've seen before. G tilde mu nu, W comma mu, W comma nu, plus 6, box conformally transform of W. Okay? Again, I haven't done anything. This guy is exactly that. Plus, I'm going to use my Lagrangian, which had G mu nu and phi. But now what I'm going to do, I'm expressing G in terms of the inverse of the conformal transformation. G mu nu is equal to that. Again, I haven't done anything. And similarly, for metal, m phi to the minus 1, G tilde mu nu, and then we have our metal field. Now I can notice something, that this guy here is actually the construction of a kinetic term. Okay? We can get the first bit, the bit number 1, so from here to here. You see we have G mu nu, covariant derivative of W with respect to mu and with respect to nu. That's a term, let's write it here. 1 and 2. So 1, it has a term, comma, mu, W, comma, mu. That's a kinetic term. Like the one that we have in a canonical, in a canonical scalar field, right? Which Lagrangian is phi, comma, mu, and then we have a potential, right? So you see it contains this term, which is a kinetic term. This guy here needs a little bit of reshuffling. So you see that we have an integral. So we have this integral with this guy here, with derivatives. And we can apply, solve this integral, or split this integral with, by integrating by part. Okay? When you do that, you get a term which has, again, a structure which is kinetic, and a boundary term that is negligible. So it's not negligible, it's 0. Okay? Therefore, both of these terms represents a kinetic term. So knowing that, what we do? We get this stuff and we try to put it together with the kinetic term of our Lagrangian for our field. So we do that. And again, we have our integration in the omega. And then we have f minus 1 right? Now I don't remember if minus 1. Maybe yes. Check in the notes, or I will check. I don't remember. Anyway, we have f to the minus 1 r tilde, which is this guy here. Okay. Plus. Now I put all those terms together, so we have to the power of minus 2 L phi of f to the power of minus 2 of minus 1, sorry, g mu nu of phi plus f to the minus 1, yeah, I think it's minus 1, f to the minus 1, and then we have 6 box tilde of omega minus 6 g nu mu nu of w mu w nu plus this guy. Therefore we have f to the minus 2 yes, perfect. Okay, m f to the minus 1 g mu nu conformally transformed, and our vector field. And this is closed with the parentheses. Okay? End of the story. I just took these two terms and I put them together. Okay? What happens here? It happens that I can define a term which is a modified gravity term. Look, this is not anymore the Hilbert-Lagrange action, the Einstein-Hilbert action, because it's not just a Ricci scalar. There is something else here. Modified gravity. Or looks like modified gravity. Okay? Then what we have? We have all of this stuff that it has. So here is a canonical Lagrangian, like that one, and we have an additional term, which is a kinetic term. All of that can be written as a canonical Lagrangian with respect to the metric, to the conformal metric. And this guy, again, is going to be tilde m, g tilde, mu, and we have phi. Now, the simplest term to see the modification is this one. So you see, we have f to the power of minus 2, and then whenever there is the metric inside, we multiply times to the f to the minus 1. So I can rename this function such that these two modifications are absorbed. Okay? Therefore, that one is going to be like that. What's happening here? We have a coupling term. The equation of motion is going to be different. And coupling to what? A coupling to phi through the conformal transformation. Okay? Now in the next lecture, now I don't want to exaggerate, I'm going to show you why this is a standard Lagrangian. Okay? A Lagrangian that can be brought to a canonical form. But that's the key idea. Okay? So let me summarize it briefly. So what we have done is to start with this Lagrangian, which is the usual one. Standard gravity, a scalar field, which symbolizes dark energy, and a matter contribution. Then what I did? I just expressed this G with respect to the conformal metric. So this guy is this guy. I expressed R in terms of the conformal R, and this guy is this guy. That comes from the expression that we've seen before. And then this one, what I'm going to do is just express the conformal, the metric in terms with respect to the conformal. And this G are these two guys together, again by the construction that we've seen before. Okay? So I haven't done anything. I just split the metric into terms. One with the scalar function f, which I call conformal transformation, and the standard metric. Good. Then what I did was to realize the fact that this object has the structure of a kinetic term. This one is obvious. Okay, that's obvious. This one is less obvious, but can be shown just by applying a derivation by part. Because you see, we have an integral of this guy that I can use an integration by part. So I'm going to have two terms. One is going to be a boundary term, which is 0. We don't care about it. And the other one has a structure of a kinetic term. Therefore, what I did, as a logic, I brought this guy together with this one. So basically, I created a modification, a new Lagrangian with a modification in the kinetic part. And therefore, I can get an expression that looks like this. Okay? Here we have a modified gravity and a coupling term. Now, have I a new theory? No, exactly. That's not a new theory. Because the total equation of motion is not changed. Because we have, on the one hand, the standard gravity with our field. Here I have a modified gravity. Therefore, the geodesics are going to be different. But there is a coupling term that compensates those geodesics. And the equation of motion of matter, having all of these together, is exactly the initial one. And the thing is obvious because, you see, I haven't done anything in 2 steps. So this is not a new theory of gravity. So then whenever you're making a modification, check that this is not happening. We would have had a modification of gravity without this Lagrangian. Okay? Later on, I'm going to show you how this is going to happen. Okay? So not a new theory. Not a new theory. Here is something important, because we are moving from a frame in which we have general relativity, and perhaps in our Lagrangian here, we have a coupling term for our baryons. But I could apply a conformal transformation, so I can choose an f such that the coupling in this term disappears for my baryons. Okay? Therefore, I can, in this frame, which is called the Jordan frame, I'm dealing with a modification of gravity, but I can get rid of coupling terms. And this might simplify my life. Okay? Is it clear? Okay. So that's what I wanted to tell you today. Sorry if it took longer. I will continue next time, and we will see why this is the case. And we're going to show you how you can generate modified gravity theory with this conformal transformation. So this would be like a step to simplify your life. You're not changing your theory. You're just rephrasing things in a different way. But you can as well use it to generate theory of modified gravity. Okay, because you are introducing a new degrees of freedom. In this case, we didn't introduce a new degrees of freedom because everything got absorbed. This field got absorbed by this Lagrangian. 1 degree of freedom only. Okay? It was just a frame transformation. Okay, thank you very much. Sorry again if it took longer.